think about whatever question I have asked. So I will hand the mic to Mridula, who will tell that what we are overview of what we are going to deal today. Mridula.
So hello guys. So this is third session of Guide to Galaxy presented by Horizon, and today we are going to see about intro to radio astronomy, and we'll see how the evolution of universe and stuff like that. So a brief introduction. Is it audible? Okay, so basically that's a radio wave signal interrupting TV or something that you see. What if I tell you that's from the birth of the universe or during the Big Bang? So, you know, the earlier astronomers, they thought that it was just the visible light that they see can be used for radio astronomy or capturing images of beautiful galaxies or star clusters or constellations whatsoever. But Maxwell came. He told that the light is actually consisting of electric and magnetic field. So he told that the light is actually spread over a broad spectrum of different wavelengths and different frequencies, and thus they people found that there is a broad spectrum. This is called electromagnetic spectrum, and astronomers were very curious. Okay, we saw images in visible spectrum range. What if we could capture images during with different wavelengths of different frequencies? So that's when people started trying to capture image with different frequencies. But as they progressed in their experiments, and they did a lot of experiments, by the way, but at a point of time they realized there is something that is blocking the different kinds of wave spectrum coming to our Earth, and that's when they realized there is something called atmospheric opacity. So what is atmospheric opacity? So basically our atmosphere blocks out most of the electromagnetic spectrum coming from the universe. Basically we'll just see a part of visible light, and then we'll see a broad spectrum of radio waves, and we can see parts of microwaves and parts of UV or IR. So this is one key point why people opted radio astronomy. So it's a broad range, and it's sufficient enough to gather information from our universe, and it's also sufficient enough to understand our universe. So today's basic concept is we are going to map our universe in a 3D format. So we need to know a different frequency of we'll take a different frequency and we'll try to capture image in that particular frequency. Alright? Okay, so this is one example. So can anyone name what is that nebula? Yeah, it's Crab nebula. So basically this all four are Crab nebulas, but the first one is taken with radio waves, the second one is, the B part is taken with optical, and the C part is taken with infrared, and the D part is taken with X-rays. So why do we do that? You can just take simply with optical, it's colorful. But every spectrum of the every frequency of the electromagnetic spectrum tells you a different information. Suppose take the C, it's taken with infrared radiation, but people found that there is something called synchrotron radiation from this. So every frequency tells you some information. So for example, the X-ray tells you that there is pulsars. You can see the perpendicular thing coming out of the nebula. So that's why people are very curious to understand universe in different frequencies. Alright. So this is another example. So Cygnus A is very important in radio astronomy. Why? Because it's the first radio image captured. So yeah, even here it's a black hole basically, and in X-ray if you see there is assertion disk. In those times it was taken around 1970s or something, and people were not even understanding what was happening. So it was very big discovery which humankind has made. And even in radio waves you can see those are pulsars. So black hole is the galaxy is somewhere here, and pulsars are spreading all over the universe. Okay, and in optical you can see it's barely visible. Nothing is actually visible, right? So that's why we have to go on to radio astronomy. So it's a small overview on what we are going to do in today's session. So first we'll talk about cosmological redshift. It's a mathematical tool many astronomers and radio astronomers used, to segregate universe in different timelines. And the next we'll see about cosmology and the evolution of the universe. Meaning, at a specific era, a different kind of radiation would have been emitted, right? So that's why it's very important to understand the evolution of universe. And the third, we'll see what kind of radiations are coming. Once we understand on what era it is being emitted, we have to understand what are the types of radiation. And next, we'll see what we have learned so far. Even though we don't know what is happening, there might be some conclusion which people would have made, right? So we'll see some part of the discoveries, and we'll finally go into the techniques. How do they even detect them, right? So, and at last we'll conclude with what's the future of radio astronomy. And now I'll give it to Kishle to continue with the further session.
Okay, just we'll start at the point where we left. So basically what did I ask from the starting is that we all know that there is something called Big Bang that has happened. But can you tell me why we believe that there was something that Big Bang happens? Is there any observable proof or not? Yeah?
Is it background radiation that originated during the Big Bang and is still visible in outer space? We can still hear it on the radio.
You are on the line, but need perfections. Anybody else? Why do we think that Big Bang has happened?
Because we see that the universe is expanding, but one time it must have contracted.
Nice. So how we know that it is expanding right now? How we know that fact?
If we observe every galaxy, we see that most of them are redshifted with respect to us, so they are moving away from us.
Nice. So basically, the tool we use to see the events in our universe is redshift. So how much it has been redshifted from the start is what we know that at what time it has been happened. So okay, I will deal with it after. Okay. So basically, can you tell me what is redshift? Anybody? You use the word that we are expanding and the light get redshifted. So anybody knows that what is redshift means?
Due to the moving galaxy, the frequency of the changes.
Okay, let me ask a question from you. So basically, I am assuming that it's some lambda. It is red light, call it red light. And call it this is also red light, but it is expanded. It's my bad, expanded, not. It is redshifted. How can we how can we know that both of these lights are different?
We can compare their wavelengths.
Both are red light only. I am observing both are red light only. So how can we make that this is a normal red light and this is something that we call redshifted. Redshifted red light. I think you get my point. What I am trying to ask. Anyone? So basically, you use the word Doppler redshift, but it is almost same like Doppler redshift, but cosmological redshift a little bit different. So basically, Doppler redshift is redshift or Doppler effect happens when something is approaching someone or getting away from this. But cosmological redshift is happening not because of that; it's happening by the expansion of the universe itself. So basically, it is a little bit different, but it's not at the same time. Okay. Okay, now let's see. So I asked you the question that what's the difference between these two? So basically, this is the main difference. Okay, see. We know that every element has some kind of spectrum. So just think that we have hydrogen on our laboratory and it will emit some spectrum. So basically, whatever I show is that this is laboratory hydrogen atom spectrum. Absorption spectrum. Fine. So when we see nearby in our galaxy, we see some star is there, and we observe it, and we try to get its spectrum. and we observe that the whole where the absorption line is there, it gets a little bit shifted. What my bad. So this is what I mean when I say that it is redshifted. So whole the absorption line has been shifted towards red wavelength of the light. So I think now you get the point what is redshift and what's the difference between both lines and all. So now let's start. Our main objective was that we want to know that when the event has happened in our universe. At the very start I asked you the question, when this event has happened with at what time. Oh, my bad, I didn't ask everyone. Fine. So basically, let's go into this. So we want that we get some light. Our receiver will just receive some light. So I have to map that this. We know that it will be a redshift because it is going far away from us. So we want that by the calculation of redshift, we want to see that what was the age of the event that has happened, of timeline of the event. So we need to do some maths. I'm going to maths now. So before that, going to maths, let me ask one thing. What do you know by what is distance? Anyone? Bro, you know that what is distance. It's not like nobody knows. Tell me. What is distance?
Coordinates of 2 points.
What?
Difference between coordinates of 2 points.
Nice. We have 2 points and the distance. So, how can you calculate this? It is x1, y1 and it is x2, y2. How do you are going to use it? Calculate the distance between these 2 points. Minus delta x square is fine. Delta y is fine. Let me ask one more question. Is it true for every time? What?
Like curvature and space time.
What the heck are you talking about? Why black hole right now?
The specific coordinate system that is defining the distance.
Let's not go into technical. I didn't understand what the heck are you talking about. Okay, let's take a simple example. There's a balloon, inflated balloon. So basically, balloon will look like this. So this is a curvature. Okay. I don't know there is a world beneath balloon and above balloon. I just live in the balloon. Okay. So on the balloon. So I have to take point to x1, y1 and z1 at z1 view. Z1, there are coordinates for this and all x2, y2, z2. When you want, it's curved a little bit.
Shouldn't there be 2 coordinates because it's surface of the balloon?
Yeah, okay. No. Fine. Okay. So when you are going to calculate the distance now. So is delta x square plus delta y square is going to be the distance between that. Tell me why?
Because like on the surface it's slightly different because it's curved.
So here definition of distance in this space, call it Euclidean space, doesn't apply the same distance is happening in different kind of space. So we need some kind of general distance idea. So I am assuming that I know you are not. So there is metric that is called. So for any space, it's Euclidean space. Now we define a metric that is nothing but distance function. Don't confuse with metric. It is nothing but distance function in that space. Fine. It's fine now. Okay. So they in whatever in our universe live, we know that our universe is homogeneous and isotropic. And from the field equation, Einstein's field equation, general relativity. So the first equation that you are showing, that FLRW metric comes. Just assume that you know that. I also know that how this come, but fine. It's fine. So this is the equation that come up with that. So let's understand this equation first. So ds square is nothing but distance between 2 points minus c square dt square. I think c is you know that speed of light. Dt is the time at very short period. So here comes AT term. So what is AT? So let's explain that. So we know that our universe is expanding. Fine. So at t1 time we have some coordinates this, and at t2 time it has expanded a lot. Coordinate is not going to change because space is increasing, not the it is going to change. At t2 time we have this coordinate. So AT is nothing but at this time this is something scaling factor that we call. At t1 time the scaling factor is 81 and at t2 time the scaling factor is 82. So this is how we relate the physical length of this universe, this time of universe, to physical length of this time of universe. Do you understand what I am trying to say? Everyone, fine. Did you understand it? Fine. So AT is nothing but scaling factor, fine. And there is dr square is just we are using polar coordinates. So di is nothing but r from the center. D theta all this okay. K. So what is K? So K is basically how much our universe is flat. So basically that is K is flatness of our universe. So you can say the curvature of the universe. Similarly that I talk about there is something curvature. So similarly in 3D we define something curvature of the universe. Just don't think about it. It is something. Fine. So I think you got my points. You are familiar with all the other terms. This theta and phi is generally polar coordinates and all. Now we are going to calculate how. Okay, what our main objective was that we get some redshift light and we have to calculate at what time, at what event it has been happened. So that was my point. This is our wave at the time of emission, TE. This is our wave at the time of observe. Fine. We know that this lambda will be different and this lambda will be different. Fine. Now let's calculate. So what we are going to define is ds square. You know that ds square is something like that. Okay. So to analyze this, we are going to use a special use a coordinate system in which both of this line comes at the same on the same angle. We can use between 2 points. We can just select one angle, one line that can connect these two. So for that coordinate system, angular term is nothing but 10 to 0. Is it fine? With everyone? Fine. Okay. So K is what? Anybody? What is the K? So it is the observed value that we observe in our universe, and it tends to 0 approximately, not 0.00 something, but it's approximately 0. So for our calculation, we are going to put it 0, and we left with this one. So minus c square bt square plus a square t dr square by 1. It's fine. And this is ds square. For those who know a little bit of relativity and all, they know that ds square is nothing but the path that is called light-like path. So we are calculating this for light, so it is light-like path. And ds square will go to 0 because it is. Is it fine with everyone? Why is it 0? 0. And the remaining will be minus c square dt square. So we are going to equate it. Can we equate it? C square dt square equals to a square t dr square. Fine. So we'll just c dt equals to plus minus at dr. Fine. We are not going to take minus. So minus just to represent that it is going into this way. So we are going for both the solution will be same. So this is going to be our solution. Everyone is understanding? I didn't do anything very big. The only big thing in the equation is this. Fine. See. So yeah.
So what does ds stand for? It's the distance.
Distance in space time, not in space only. Space time.
So light does travel some distance in any space. Right?
Space, not in space time. It doesn't cover any distance in space time.
Okay. We have like some intuitive understanding of why it is.
Okay. I don't have till now, but let me think a little bit. How can you make you understand?
So,
I will tell after the session, fine? I will think and just tell. Till now, I mean, anything else? Anything else? So we come up with this equation. So CDD is then TD equals to 1 by C AT dr. So we have two waves again. So this is the number TT, time TT and T naught. Fine. So we are going to calculate for this part. At what time and what was the scaling factor and all. We will calculate for this part and we will just minus. So the distance will come delta lambda that we know, that we required for redshift. I think we got. Let's do it now. Okay. So I will just integrate this from what from TE to T naught. So this will go from this T to T naught. This will go from this to this. Call it R1 to R2. Fine. We are calling it R1 to R2. So we will do the same integration for this crest. TE plus delta TE. T naught plus delta T naught. So C by KT dt equals to, so okay, let's this we call it R3 to R4. Yeah. Fine. These are two equations we come up with. We'll just minus these two equations. What will happen? So for left hand side, TE T naught C by dt alpha T by right. dt minus dt plus delta T naught equals to what? So okay, what is this? From here to here. No. If I reduce, fine. What is this? From here to here. When you think, what's the value of this? Just tell me. When you minus this. Okay, let me make this more into different. This one has PE. So PE, T naught. So from here to here is R1 to R2. From here to here is R3 to R4. When you minus these four distance, what will come?
Lambda minus lambda.
0. Is it fine? So the right hand side will become 0. Is it completely fine? Okay, fine. Now let's go to this. Let's see by when I will minus this. So we can tell that C D into T naught C by alpha. I just remove. Fine. Fine now? I just write this equation again. Okay, come here. So what is alpha T? 80 or alpha T, my bad, 80. What is 80? Scaling factor. So scaling factor happens from here to here, na? So during that time, I can assume that scaling factor, it's too far, it happens too fast that at that time, scaling factor is almost constant. Can I assume that? So we'll just remove this out of the alpha t. Integration is still inside. dt t to t naught minus integration of 1 by alpha t naught. dt plus delta t. T naught plus delta t naught. It's fine. I didn't do any mathematical mistakes. It's fine. Yeah, fine. Ask.
Why is R1 minus R2 minus R3 minus R4 0?
It should be lambda minus lambda.
Yeah,
No,
exactly.
see.
Don't it make a difference?
See, when we so okay, fine. We will come here. Integration of path from R1 to R2. What does it mean? Like traveling here from here. Fine.
Okay.
R3 to R4 for the next traveling here from here. Doesn't mean it's whatever happens with this crest will happen for this crest too. So in whatever in space and whatever distance it covers, crest 1 will cover the same.
Not necessarily.
Why not? So we say that it gets a little bit redshifted. Just think about this. There is nothing special about this crest. Just think a little bit. Maybe.
But if it's redshifting, the wavelength is increasing.
So okay, for this too, it will be a little bit redshifted. I call it. This is a little bit redshifted. Call it there. So this will happen again is the same. It will redshifted at the same time, at the same in the same space. Just think. We will deal it. I will make you understand after this session. Fine. Just assume that it is 0. Fine. Okay. This. Okay. We come up with this equation now. Everything after that is fine now. Now, okay. I will just. What is t? Let's use some graph. So we have t plus delta t, t naught, and delta t naught plus delta t naught. These are 4 timelines that we need. So for t, this was the case. We have to integrate from here to here. So we need this equation, this kind of area in the integration. So okay. So can I write this area, whatever we need is PE integration of PE to T naught plus T to T naught plus T naught to T naught plus delta T naught minus T to delta T plus delta T. Tell me, can I write this equation, this in this? Are they same? Same now? So in this equation, I can cancel out this with this. Fine? Fine. You know, I just conclusion is more important, but still. So what was my final question is? T naught plus delta T naught and T to delta T. Fine. So final equations come right now. We will integrate and do that, and we see that 1 by alpha T naught into delta T naught equals to delta T alpha by delta T. Fine. Delta T naught T my value. Fine. So this is the final equation. We will just multiply C, and we will see that it is nothing but lambda. So C delta T naught. This is delta T naught, no? This is delta T naught. T, my bad. At time of emission. It's fine. I think I'm fine. Okay, fine. So this will be lambda. So here is we do have something lambda naught by lambda T equals to alpha T naught by alpha T. So fine. So this is the final equation. Let me remove. Write the final equation. Lambda naught by lambda T is equals to alpha T naught by alpha T. So this was the final equation we will come up with. It's fine. So So we know that alpha is nothing but scaling factor. So scaling factor is what? We know that our universe is monotonically increasing, expanding. So scaling factor should be a function of time, and that is always increasing. Is it fine? So this term has some function of time. This is nothing but lambda. We can just write it now. So redshift is what? One delta lambda by lambda. Do some manipulation, we will come up with this equation alpha T naught by alpha T. Do some manipulation. I think you will. It's nothing but lambda naught minus lambda E. So put lambda. So 1 minus lambda naught lambda E minus 1 equal to Z. Lambda naught lambda E minus 1. Okay, this is Z plus 1. So this will become Z plus 1. Fine. So let's see what this equation tells.
C delta T is not delta lambda.
Not delta lambda. I'm not saying it's lambda. C delta T.
Sorry, it's not lambda.
What I see is the best focus.
No. I mean, if you take C delta proper time and not C delta time coordinate for measuring proper distances.
Okay. See what I'm telling is this at T time it emits at the T plus delta T times it emits second wavelength. What's wrong with this? It's okay now? I think you. Fine. Okay. So this was the equation that we come up with. So what does it say? Let's. So it says that we are observing some signal, and if it is call it 2, we see that redshift is 2 times that. So it is 2 times redshifted. So Z value is 2. So we can say that from this property we can say that our universe has expanded 3 times when the light was emitted. You understand what I am trying to say? So we get some wave. We get some wave, and just we say that it is shifted Z equals 2. So we say that our universe has expanded 3 times more than it is used to be at that time of emission. So here one cool fact is that, do you know what is the radius of the universe? Cool fact.
93 billion.
What?
93 billion years.
It's a diagram.
Observable universe.
It's diagram. 48. Call it 48. Some 48 billion.
Billion light years.
Billion light years. How do we know that it is? And we know that our universe is just 13.6 billion years age of universe. 36.6 billion years. How you can expect that light from 48 billions come to our side, whether light covers only if you cover, even you start with light speed of light, it will the observable universe has to be only 13 billion years something, but whatever we see is that this. So this is the fact of this equation only. I think you got the point. Is it fine? Okay, it's just intuition of what is redshift, and it is important in cosmology, very important. So that's the whole part. Now let's go to next how our universe evolved. Okay, so Big Bang happened. We know that from the redshift. We just don't know that. We know the fact that how it happens. So Big Bang happens. So after Big Bang, Big Bang happens at this single point. That's one concept, but it happens at a point. Okay, so when it expands, we don't. So first era comes is Planck epoch. So during this era, universe was too small that it needs quantum gravity to make them understand what physics is behind it, beyond it. So during this era, we need quantum gravity, and we don't have, and other theories too at that small period, at that small distance, and there are other theories too that we don't know. So we say that before this time, universe was too small that we can't explain it using our physics theory, whatever we are. So that's Planck epoch. But we know one thing for sure, and that is that all the basic fundamental force. I think all of you know that what are the fundamental forces: strong nuclear force, weak nuclear force, gravitational force, and electromagnetic force. These all forces are united. So is it fine? We know that for after that our universe expands and becomes a little bit more cool. and it lasts from after 10 to the minus 42 to 10 to the minus 38. So what happens was that gravity gets separated from the fundamental force. Well, my fundamental force nahi. Gravity gets separated from that super force, whatever that force is. So can you ask a question why it gets separated or something? Ask, bro. You should ask this question.
No, what does it even mean that they were combined?
You can't see that between those two. So let me take an intuition example. Anybody have played speed roulette or something? Spin roulette. So okay, in what is that? You have a giant circle. You have a wheel. You just put some balls on it, and it lands on something, and you can say that. So what is that? You have two balls. Okay, fine. You have two balls, and you just spin it. So before coming into rest, before stop spinning, can you distinguish between those two balls? Can anybody distinguish between those two balls? Those two balls are identical. But once it stops, you can say that one landed on 3 and one landed on 4. You can say that now, once it stopped. Similarly, so at the time of spinning, it has high energy, so that you can't distinguish between those two things. So at the beginning of the universe has that much energy that you can't distinguish between gravity and whatever other fundamental forces are. I think you got the intuition point.
Okay, how do you know like the exact time when all this happened?
Mathematics. I don't want to go in mathematics, that's an issue.
The smallest, like the only quantity you can form from the basic
Okay.
constants of inflection. You can write like a text.
So this was the time. Now, once grand unification epoch ended, so gravity got separated. First, gravity was that gets separated. Second is one more point. So we have find that when the energy is high, so weak nuclear force and electromagnetic force starts to you can't distinguish between those at the high energy level. We have found it in laboratories. So that's one of the evidence that it can happen. And one more thing is that even mathematically strong nuclear force is consistent with these results. That at high energy point you will strong will also behave similar like those. That's the fourth point. So one comes electroweak epoch. So this was the time that I noticed. Fine. So during this time, the strong nuclear force gets separated from the fundamental super force. Fine. Next is inflationary epoch. So basically, what is inflationary epoch is that before this period of time, we believe that Big Bang causes a linear expansion of universe. Before this, we believe that kind of linear. But during inflationary period, what happens? The Big Bang universe started to expand exponentially. It was too high that the total volume of the universe get 10 to the power 78 times in just fraction of time. So you can tell that a small DNA, you know how much small is that? So DNA expand 10 to the power 10.3 light years in that only fraction of time. Just think, it's too high. Fine. So this was inflationary epoch. You can ask that why did it happen? Why do we need this to happen? There are some problems with Big Bang theory. 3 of the problems are horizon problem, what ours. Second is monopole problem, and one is flatness problem. I want to go in detail, but I don't think so time is there. But I will talk a little bit about horizon problem. What was that? Because it's our problem. Fine. So with Big Bang theory, there was. So I told you now. So call it. Universe. So do you know about CMB? I will talk about a little bit later about CMB, but just think that you know about CMB. So the information CMB contains that almost universe is almost same temperature difference is almost 0.001 Kelvin at the highest point of the universe at highest temperature at that time of universe and coldest temperature at that point of time universe was almost 0.001 Kelvin. So it means that everything was in thermal equilibrium. during that period of time. Whenever CMB released, whenever that wave released, our universe was in thermal equilibrium. So when we calculate with the Big Bang theory, the radius of the universe at that time, we found that it was much more. So to be thermal equivalent, I want to take 1 minute more radiation. Right? So we are a bunch of students, and today is our test, and I want to cheat, and the whole class wants to cheat. Fine. So what's my issue is that I know everything about this. I will transfer my information to him, and he will do that same. So last man to know is the last one who will know will take 10 minutes to do. It's 10 minutes, and he will receive the information. Fine. So he will know after 10 minutes, whole class knows that what's the answer. But examiner comes in 5 minutes. What will happen? Only half of people will know that what the answer is. But the issue with CMB was that even examiners come at 5 minutes, whole class knows. Means light has saved the information from there to this part of the universe to this part of the universe in less than time that Big Bang theory predicts. Did you understand what was the horizon problem? So traditional or classical Big Bang theory can't explain this. So we have to introduce inflationary theory in our Big Bang model. I think you got the point what I want to tell. Okay, fine. After this was second electroweak epoch. So during this period, before this period, one other thing is that we know a sort of why inflationary epoch has happened. So there was a theory that during this time, when the strong nuclear force gets separated from the fundamental superforce, called it superforce, this can initiate the inflation to happen. So this was one of the theories that I want to say, and that's it. So after that, electroweak happens. Electromagnetic and weak get separated from each other. That's fine. Now all the fundamental forces are separated now in just 10 to the power minus 15 seconds of the Big Bang. In just a small period, all the fundamental forces are ready to cook. Fine. So after that comes particle era. So we have a lot of energy, and from Einstein E equal to mc square, we know that energy can convert into mass and mass can convert into energy. So for I want to do it first. Okay, fine. So during this period of time, particles started to create the universe. Fine. It gets. I want to tell. Okay, fine. So during this period only, all the particles come into existence in our universe. So whenever particles comes, so I want to tell there was something particle pair production stuff. So what happens in this experiment was that they was having PS, we bombard heavy energy photons on it, and we see that it gets converted into electron and positron, and it gets into positron. Right? It is one of the experiments. To understand this, we need quantum relativistic theory. So I am not going to detail. I will just tell you the so in this experiment, what happens that this photon gets converted into electron and positron. It's fine. So we can say that from energy we get some particles. Similarly, in the early universe, it can happen, and we can create a lot of particles from that. But with particle problem, that antiparticle has to become into existence. So particle, antiparticle will be there in our universe. They will start to annihilate each other, and release lot of photons in our universe. But during this process, due to some quantum fluctuation, some matter didn't get annihilated. Fine, due to quantum fluctuation, and this is going to create the whole particle and matter in our universe that is in existence till now. So we are just part of quantum fluctuation. Fine. Okay. Fine. After this, so these are different quark, hadron, lepton, photon, I don't want to deal it in brief. I'll in detail because it will take a lot of time. So just you can see this slide and tell. So one thing. After the end of this era, what we do have that we have electrons, protons, neutrons, and everything that we need to make our universe. So here, so at this period of time, 2 to 20 minutes after the Big Bang, what happens that? Thank you. What happens was, so all the electrons, all the protons and neutrons, whatever it is, started to form a system that we call nuclei. So this was the nucleosynthesis era, where 25% of proton and all the neutrons used to form deuterium and different neutrons, nucleus of different atoms. Not more complex nuclei, but starting with the nuclei. Now at the end of the era, we have nucleus, electron. Now let's go, we can make atom. But the issue is that temperature of the universe. Our temperature is too high that before founding the system that we call atom, the electron has split energy due to temperature is very high because. So we need our universe to cool more down. Okay, now let's come. So after a certain period of time, about 370,000 years after Big Bang. So now our universe is cooled down that this much cooled that electrons can no further escape from the electric field of nucleus, and they started to recombine. So what happens that we are going from higher energy state, that is electron from Bahar, to lower energy state that form atom. Fine. So during this period of time, what we will expect that photons to come. Some energy should be released. Now we are going from higher energy state to lower energy state. So some energy should be need to be released. So that energy is they emitted in light energy, and that's photons. So this is what we see when we go to, and it is photons. We know that hydrogen spectrum consists of visible rays, but due to redshift, so all that visible and ultraviolet range, but due to redshift, it all it gets shifted to the microwave. So the weird microwave comes from there, and we know that this is the size of the universe. It emits everything selected right now, and even if it gets big, it will be at all places in our universe. So it is in background of everything. That's why we come up with the name cosmic microwave background. So this was this cosmic microwave background contains every information about a lot of information about that period of time. So this was cosmic microwave background. Now comes we have cosmic microwave background, and it gets redshifted. Redshift means energy should be less. So what happens that electrons and protons with this. So we have atom. It is getting redshifted. So when it will try to interact with this, it won't, because it don't have that sufficient energy to interact with the matter. So what we left with in our universe is neutral hydrogen, some deuterium, some lithium, and some helium. I am just calling neutral hydrogen. So during this period, our universe consists of only neutral hydrogen, and we don't have information about this. Because light didn't interact. How we see that light interacts with some matter and it comes into an eye, and we observe it. That's it. But the light during that period of time doesn't interact with any matter that was present. So during this period of time, we don't have any information about the universe. But we humans are intelligent person, clever person. So we have come with some ideas. Fine, I will discuss it later. So after that, what happened that once we have neutral hydrogen, everything started to collapse, gravitationally collapse, because we have fundamental forces and all. It started to collapse on its own. First star forms, and it started to reionize. So energy comes, the photons from this first star started to reionize all the hydrogen present in that universe. And after that, we know that what happens in our universe. But the question remains same, that how to map our universe in the era of dark ages. Is there any solution? What? Oh my bad. Is there any?
I mean, there will be gravitational interaction of light as well, right?
I don't know.
It won't be that useful, but like, it will be something. Give us something.
Okay, for doing this thing, we need radio astronomy. How will this solve this problem? We'll talk a little bit later. Now I will call Mridula to tell a little bit of radio astronomy. So I will handle my microphone.
So, alright, so we have seen in different era there was different kind of radiations, and Kishle told that there was like different processes which involved. Everything is basically radiation, but the process which it takes is different, right? So similarly, there are different kind of radiations. So now our universe is filled with a lot of radiations. So we'll see. So basically, radiations is segregated into three types: thermal, non-thermal, and then spectral drying radiation. So in thermal radiation, so first thing when I tell thermal radiation, which comes to our mind is black body. So what is a black body? What is a black body?
Black body.
That's not what it is.
Hypothetical object that can absorb all frequencies of light.
Nice. So it absorbs light and it emits light, but it doesn't do any action like reflecting or transmission. It doesn't do this kind of activity. So suppose take a mirror, that's not a black body. Alright, so now it's just a basic definition of what is a black body. So now Planck came with a equation which defines the intensity or the brightness of that particular object. So when I tell black body, it seems very fancy, but everything around us is kind of a black body. Even me, you, everything is a black body. Alright. So now the first equation is a brightness, equation. The brightness at all frequency at a particular temperature. So this is what generally that equation is meaning. And Wien's displacement law is basically tells you at what particular frequency or wavelength that particular black body radiates at a high temperature. Okay, basically we are finding the peak value. Okay, and then comes Rayleigh's-Jeans law. Even this holds for black bodies which emits in the lower frequency. Alright, so why am I randomly putting three equations? So first thing why it is very useful is, suppose take an object, okay, suppose take a star which is emitting at a frequency of UV rays, and by mistake we thought everything is radio wave and we designed an equipment which only calculates radio wave. That's not right? So we have to know what is the peak temperature or the frequency which it emits. So that's why Wien's displacement law is very important. And black body radiation, the Planck's equation tells a general equation about all the black bodies, even it's cold, hot, whatever it is, high frequency, low frequency, it applies to all range. And Rayleigh-Jeans is very useful when it's like mathematically reduced equation especially for radio waves. Alright? So this is a general information about all three equations. And it's also very simple to convert from Planck's equation to Rayleigh's equation. So you have the this equation, right? 2 Hertz Q by C square. So this can be expressed as 1 plus, we all know the Taylor series expansion and stuff. So this 1 and the minus 1 gets cancelled off and the frequency is very less, and that's why this h mu by kT term remains in the denominator and we get that equation. Alright. So one important example of thermal radiation is cosmic microwave background radiation. So Kishle was talking how this radiation is being emitted, but it is all a thermal radiation. And one more important example is infrared radiation from dust, stardust or molecular clouds. Basically what they do is they absorb the energy coming from the universe. The dust on its own doesn't emit any kind of radiation. They absorb the radiation which is coming from the universe and they emit in the thermal spectrum. Okay. And the thermal radiation is also very important to determining the size and temperature and energy of that particular celestial object. Okay. Next is non-thermal radiation. So this is also a very important discovery in radio astronomy. So first thing they ever observed is this non-thermal radiation. People at that time were thinking only thermal radiation existed in our universe. But there was also non-thermal radiation such as synchrotron radiation and Bremsstrahlung radiation. Name seems fancy because that's a German word, Bremsstrahlung. So whenever there is a magnetic field and there is an electron, a relativistic electron. What I mean by relativistic electron is an electron traveling at the speed of light. Okay. So this electron, whenever it passes by a magnetic field, it gets deflected. Okay. And due to this deflection, there will be some sort of radiation. So this is synchrotron radiation. And similarly, we know there are two fields, magnetic and electric field. So we have seen when there is a deflection due to magnetic field, that's synchrotron. When there is a deflection due to electric field, suppose there is an atom, this is nucleus, and again a relativistic electron. Relativistic electron is nothing but our, the radiation or the light coming from different celestial objects. Okay, so this radiation comes by this atom, and it gets deflected due to the electric field present in this particular atom. And due to this deflection, it loses some part of its energy and that comes out as a radiation. So this is Bremsstrahlung radiation. So it's a German word which in English it means breaking radiation. We break the radiation. Okay. So this is about non-thermal radiation. So why is it important? So do you know this? Yeah. This is Orion Nebula. So basically it's a Bremsstrahlung radiation. Okay. And why are we interested in this? The planets, the sun, almost all the celestial objects have its own magnetic field. And we know the universe is already filled with a lot of radiations. So obviously there will be a lot of synchrotron radiations. Alright? So the next one is very, very important. I'll call Kishle to explain about this.
Okay, thank you, Nidula, who talked about what is the radiation, what kind of radiation we are seeing in our universe right now and space, to be honest. Okay. Okay. Now let's where we end our talk was that how we know about the dark ages. Now that's our question. So what I told you that no photons are interacting with the hydrogen that was present at that time. But I didn't talk about that whether hydrogen is emitting some light or not, photons on its own or not. So after a long time, we come up with something that do you know about the hydrogen's this transition energy? So this is alpha 9 Lyman-Barber question. So during that time, we know that no photons are interacting with it. But as your science improved, we came to know that even every transition lines consists of two different energy levels. So this is basically okay. Now let's talk about what is this energy level. So let's hyperfine structure. So what happens in atom is that we have a proton, call it plus charge, in a hydrogen proton, and we have an electron. So there is quantum mechanically defined spin. Don't think that it is spinning on its axis, but we can take analogy a little bit like that. So once any charge is spinning, can you think that it has some kind of angular momentum? because this is mass that is spinning on its axis. Fine. So it will have, it's not that spin, I am doing literally very in a wrong way, but we can assume that it is kind of spinning. So it will have some kind of angular momentum. Electron will have its own angular momentum too. So I think you all have studied in JEE that this formula U is equals to Q by Qm. J is angular momentum and this is magnetic moment. Okay, I can derive, but you should also derive if you have done the JEE. So once it is spinning on its axis, it will have some angular momentum which consists of some magnetic moment. And we know that electron is here to create a magnetic field. So there should be an energy that will be defined as minus mu dot B. I think you note this point. So when this spin is in the same direction or parallel, so it will show energy level of different and when it is different energy level and when it is in different unparalleled state, it will show some different energy level. So we have that same electron is there in the first cell, first transition point, will have two different energies, and this energy is very small. So hydrogen at that point of time will also have the same electron, I think at hydrogen they have the same kind of electron. So this energy is too small that even a small collision can cause the electron to jump from this to this. So hydrogen at that time of universe had the same thing. They should have jumped from one to here, and during this, when it will come, because it is more stable state, it will come back to the stable state and emit some energy. It's fine. So it is in photons. It will emit some photons. So 21 centimeter is nothing but just the study of these photons at that period of time to map our universe in diagrams. So that's the 21 centimeter. So okay, yeah.
Why is it called radio?
Yeah. So basically, when we calculate this energy, and we will know that every photons have their wavelength, so it will something else, 16 on something. But it is shifted in that much. It is from the past, so it has to be redshift. So it is redshifted at that point of time that it becomes 21 centimeter. We observe it in 21 centimeter. And 21 centimeter consists of is study in radio wave part. So we need radio astronomy to understand our universe in that period of time. I think it makes sense now. Now I will call again Mridula to talk about.
So now we have seen different types of radiation and what are the process which creates these radiations. Now we'll see what are we actually measuring. So first term, when someone thinks about a light emitting object, it's brightness. When I tell this light is brighter than this, how do I measure it? What is the quantitative measurement? So okay, first thing is if I tell a 100 watt bulb, so what does it mean? Yes. So it emits 100 joules per second. That is what it means by luminosity. So luminosity is just calculating the light energy emitted per second. This is what all we wanted. We want how much is the energy that the celestial object is emitting. Right? This is the basic quantity which we wanted to measure. But it's kind of more, we need more sophisticated instruments to measure these luminosity directly. So we shifted to some other quantity called flux density. So how do I tell flux density? So suppose this is up. Okay, so luminosity is just, defining the star. Okay, it's just some watt, it's emitting some energy in watts. Now these radiations, if I set all over and I take a small area of cross section and one more here, same area but in a different distance. Okay, so now flux is calculated by telling you that the luminosity divided by the spherical area it covers. Okay, so now if I take this area, there will be a lot of flux. You see that if it's nearby, it has a lot of flux, and if I go farther and farther away, the flux density decreases. Suppose I have two astronauts here, or maybe different planets with different alien species. We are here and that alien is here. Okay, I'll draw it. So that alien is here and we are there. And both wanted to calculate what is this celestial object, what is the luminosity, and they tried calculating using flux density. Now both will get different values because one is nearby and one is farther. But this shouldn't happen, right? It should be universal. Wherever it goes, this celestial object is defined, right? It emits a particular energy. And so we wanted some other quantity to define it universally. Okay, so that is when people introduced the specific intensity. So what I do in specific intensity is the same. I'm here, or we are here, and this is the star which is being emitting the energy. And now this is the distance from star, and this is the radius of star. The star, and then this is the first astronomers or us radius from the star. Okay. So now I'll calculate theta. So since we are very far, I'll tell this theta will be approximately equal to Rs by R1. Okay. And then for the alien species, be similar, just that the distance varies. Right? So the theta 1 is Rs by R1 and theta 2 is Rs by R2. Okay? And now these both came up with the conclusion that when we divide the, something called a solid angle, when we are in 2D it will just a theta radians, but when you go to 3D it's steradians, meaning solid angle. Okay? So now these people, what they did is, they took a quantity which is taking the flux 4, 5 R1 square, and they also divided solid angle. Okay, solid angle is just pi theta 1 square. Okay, so I divide pi theta 1 square, which is nothing but R square by R1 square. So these two cancels out, and what remaining is LV by 4 pi square into R square. This is for us, or the astronomical point. Okay, and for this also we'll take LV by 4 pi R2 square into pi RS square by R2 square. Right? Again it cancels out and we get the same quantity. That is nothing but LV by 4 pi square by RS square. So now it's universally defined. So this quantity is called specific intensity. And also there is one more important thing. If I measure a light and people, okay, they accepted this fact, and there was one other problem. Suppose I have a red light and I have a blue light. So now comes another problem. So you have to define the frequency. So they thought they'll just, again dividing the frequency will give me the specific intensity. Okay, so people will call it brightness or they'll tell specific intensity, both are meaning the same. Okay, so this is what we are actually measuring. And now let's go to some history part. So there was this guy called Carl Jansky. He was a very curious antenna designer during World War II, and they were asked to do a lot of communication. And that time when he was during the World War II time, he observed a very steady hiss. And this his seems to be diurnal. What I mean by diurnal is it occurs 24 hours a day. And during World War II, he obviously couldn't do anything or research about it. So once the World War II has ended, he started observing that his. And this his seems to be not 24 hours. After a year of experiments, he concluded that it occurs every 23 hours and 56 minutes. So what is 23 hours and 56 minutes? Yeah, the full rotation of Earth. Meaning, so this is how it goes. This is Sun and this is our Earth. Okay, it suppose initially Earth was here and it started, rotating on its own axis. But we know there is something called revolution also. So by the time it rotated once, it might have gone here. So that is why we tell it 24 hours, but then it's actually rotating 23 hours and 56 minutes. So now it's obviously not Sun. First he thought, okay, 24 hours, what comes and goes? Sun. Now it's not Sun. What might it be? So it's just the celestial objects. What remains constant now for 23 hours and 56 minutes because of a rotation of Earth is other stars and galaxies or whatever it is. So he told that there is something which is coming from space and reaching us, maybe from some other galaxy too. But then he couldn't continue his research, and that's when Grother Reber came. Yes.
Why are we ignoring the sun? Like you said, this happens once every 24 hours, but why are we ignoring the sun?
Yes. So after a year, he concluded that it is occurring every 23 hours and 56 minutes. So now our Earth revolves around the sun. So when you don't take sun, only you take the Earth, it rotates only 23 hours and 56 minutes. And due to the revolution, we tell the sunset and sunrise happens 24 hours. So that is why he concluded, now it's not 24 hours. He calculated that it is occurring 23 hours and 56 minutes. So what it could be, it's not sun. He also found that when it was day, he was not observing anything. And when it was night, he was observing some steadiness. So it's not Pakka sun. So he thought it might be some other objects. So now the stars are very far away, so it seems to be constant in the sky after every 23 hours and 56 minutes. So that's why he told it might be from some other galaxy or some other celestial objects. So now this person continued his research, Grother Reber, but okay, Jansky was working in Bell Laboratories, so Grother Reber also wanted to join the same laboratory and continue his research, but they were not very interested in giving them. So he installed a private single dish antenna in his backyards and he started observing the radio waves. He told that he confirmed Jansky's discovery, and he also pointed out there are some radio stars which we cannot really see through visible range. And these radio stars, and he got more signals from the constellation Sagittarius. So where is Sagittarius? Does anyone know? Sing. Yeah, nice. So Sagittarius is a constellation which is present in the center of a galaxy. Today we know that there is a lot of supermassive black holes, but at that time they didn't know. So this is the first very important conclusion, that there are a lot of supermassive black holes at the center of every galaxy. He also tried to map our universe, so that's the picture which he concluded. So next important discovery is about dark matter. So everything, other things were very obvious, but this dark matter needed some proof to confirm its existence, right? So now we take a galaxy and we confirm that there is a lot of supermassive black holes at the center of the galaxy, and thus the mass in the center should be higher than the outer layers, right? And according to the Newtonian physics, we should tell that g mm by r square should be equal to mv square by r, right? Just the gravitational force and centrifugal force are getting equalized. So now this velocity is nothing but from any particular r, what is the velocity at that particular radius, okay? So now according to Newtonian, it should be v is equal to root over gm by r. So when we try to plot this, we might be getting something like this. So initially there is a lot of mass at the center of the galaxy, so there is a increase in the graph, and as it goes on the radius becomes very huge, that the mass decreases. It's just a parabolic curve after a long distance. Okay, so this is a theoretical model, but with the help of 21 centimeter, as Kishle was talking about, we observed that the graph seems to be like this. So why does this happen? So this is when they concluded that there is something called dark matter or dark energy. So this doesn't interact with any matter at all. So even light, it's not visible in any part of the spectrum. So even now there is a lot of study going on dark matter. So this is one of the very important discovery. And the other one is that the galaxy interactions. So normally at that particular point, people were trying to focus on that particular area of space, but they didn't see anything. But using radio waves, they found there are a lot of galaxies interacting with each other. So we have seen how radiation has been emitted in one particular era to the other, and we have seen what are the types of radiations. So this is like all the stuff we have done, but before going to what are the techniques we are using or what are the instruments we are using, I wanted to tell you that if there is two accelerating charges, there will be the radiation produces. So so the charges continuously accelerates and decelerates. So this is normal electric field. But as it moves, as you know that even electrons, protons move at the speed of light, it cannot, infinitely, at an infinite time it cannot transfer the information. So we expect the field to be like this. But instead we get a kink at that particular point, because there need to be a time for that information, for that particular information to get transferred. So this is how the electromagnetic radiations being produced. So there is a wave. Okay? And now we use the same concept and we do it in a equipment. So antenna itself is a huge study. It itself needs to be done with a lot of efforts and a lot of courses. But here I'll just show you a brief on how antennas work. Suppose you take a conductor, just a normal conductor. This is a normal conductor, and there is this wave passing through. And for each peak and each, as the waves, the sine wave increases and comes down, the electrons moves up and down. And now this is called as dipole antenna. Okay, so this dipole antenna, so instead of just having a single conductor, they measure this electric field into voltage signals. So this is how for practical applications they collect these electric fields and they convert it into voltage signals. So this is the animation for that. So as you see, so this is very easy to construct. It's very cheap, feasible. You can do it at your home also. But there is one negative, very very important negative, point on it. So if you want to discover the light of wavelength 300 meters, you should have a conductor or this dipole antenna of length 300 meters. Why? Because you see that initially the electron starts moving, and as the wave moves, it comes down. So we need to have this oscillation or the acceleration between charges from one end to the other end. So that is why we need this big antenna, dipole antenna, to be at the size of wavelength of that particular source. Okay, so this is This nowadays people use this, even this is importantly used for observing 21 centimeter, but for a lot of years and a lot of researches are done using other antennas. So the other type of antenna is single dish antenna. Yes.
Why should it be, if it's 300 meters, why should it be 300 meters now?
Yes.
Like if it's not, even if it's 15 centimeter out of 300 meters, you can sense the electron moving here.
Electrons move, but you won't recreate the same electrical signal into voltage signal. Our motive is to recreate this electrical signal into voltage signal. If you change the distance, this starts moving after every now and then, right? So the signal comes and goes. This starts moving with a different frequency. This electrons accelerating will produce its own voltage signal with its frequency. We want this frequency and that electrical signal frequency to be same. So we want to exactly recreate what is coming. We don't want to add or lose any information, right? So that is
a matter of efficiency. There is a particular dimension of the dipole. For a particular wavelength, it will be very efficient. If it is larger or smaller, it will be not. This is why we need a particular dimension.
So next type of antenna is single dish antenna. So this many people would have known. So there is a parabolic dish, and all electrical signals or waves comes and fall onto this parabolic dish. So what happens in a parabola?
It started to the axis, convergent the focus.
Yes. So there is a focus here. So whatever waves coming on, so it hits the dish and focuses at that particular receiver. And we have a receiver, it has its own mechanism, it has a lot of things to collect the data. So this is one which people next thought about when it comes to antenna. But one negative point is that, so talking about angular resolution, we all know that angular resolution is this formula been studied in so much time. So first, they built a telescope or antenna called Green Bank telescope. So this has a resolution of 25 arc minutes. So what's the resolution of our human eye? It's 20 arc minutes. So that's not what we want. We want a nice, colorful image as we take in optical region, right? If we take a blurry, it's like just seeing through eyes. That's not very useful. We build so much huge, it's almost 100 meters. The diameter of that particular telescope is 100 meters, but still the resolution is very small. That's not all we want. We want a better resolution, but it should also be feasible. So this is one example where they built that telescope, and due to so and so reason, after a few days it collapsed. So it's very bad, right? So that's when people opted a very interesting technique called interferometry. So when I tell interferometry, does it remind you of something else? Huh? LIGO. Okay.
It depends.
Okay. So it's the word like interference and interferometry. People opted this technique from interference. We'll talk about that. But generally, what is interferometry is, instead of building a huge telescope or a dish like this, we split that dish into smaller and smaller parts. And now I take the same amount of focuses at a parallel line to this. I keep each receiver at this parts. Okay, now I can shift these parts or arrays into a line. I can build this on a large scale. Right, this is an overview. You can see in this image, they cut this big dish into smaller and smaller parts, and they move that in a horizontal plane. Okay, so I have been shifting this term from telescope, antenna, dish, array. So what should I call them? Even I was getting a lot of confusion. What should I call this? Telescope, antenna, element, dish. So okay. So the basic difference is, if you see a telescope, it's a huge system. It consists of antennas, it consists of receivers, it does the the image processing, and it gives you the final image. The entire system is called a telescope. Okay, and when I tell antenna, it just means maybe dipole antenna as I have discussed, or the dish antenna, and specifically dish means a parabolic reflector. Okay, and an element means, as we have seen here, we cut the big dish into smaller and smaller parts. If I split these into a horizontal plane, we get an array of elements. So that's why, and each part is called an element. Okay, so that's the difference between all the four terms. And yeah, so I hope you remember about interference. So I'll just quickly remind you of what interference is. I assume you remember it. So there is a slit, there is an the observing thing. Here is the source, and this is B. This is capital B, and fringe patterns form all along this plane, and this is Y. Okay, so these are the terms which I have been used in that equation: theta equal to y by d equal to lambda by small d. So you all remember how that came? Yeah, so fine. So this is split distance, and okay, so the fringe pattern keeps changing if you move the source. Right, if you keep shifting the source, the fringe pattern also seems to change. But in case if the split distance is very large, and if you try to shift the source, the fringe pattern appears to be almost same. So whenever it's lesser in length, the fringe pattern is different. Okay, so that is one important thing. So we'll compare this with the interferometry. So what have we been adopted from interference? First thing is baseline. So we don't call this a split distance. Instead, people keep here two antennas or telescopes, and this distance they call it baseline. So you have seen there is an array which is being kept in the horizontal plane. So each element's distance will be called as baseline. The second thing which they seems to adopt is that if you take a galaxy or a star, each point is an independent source. Okay, and another thing which is very important is that additive and multiplicative. So when you take an interference, we just do it in the visible range, and thus we seem to have an equation like this: a1 square plus a2 square plus and multiplicative 2a1 a2, right? So you remember this? You just send two waves coming here, and then with an amplitude a1 and a2, and here you have cos term. So what produces this fringes? This multiplicative term. So in interferometry, what they do is take two telescopes, collect individual data, and they multiply it using a software. Understood? Clear? So, okay, one thing when they discovered this, analogy with interferences, this guy calculated Betelgeuse angular size. So how do you calculate anything of any object's angular size? This is suppose Betelgeuse. So what is a Betelgeuse? I hope everybody know Betelgeuse. Nice. So I calculate the distance between them, and then I calculate the particular wavelength it hits me. Okay, and you will be able to get the angular size. So now what this guy Michelson did was, he took two mirrors instead of antennas or telescope, because it is cheap. So he took two mirrors and he pointed at the direction of Betelgeuse, and he tried calculating the fringe patterns. And he observed this at a particular wavelength of 550 nanometers. And the baseline distance was 3 meter. Baseline I mean is this split distance. Okay, so the baseline was 3 meters and the lambda was 550 nanometers. So now with using this, he calculated Betelgeuse angular size. So actually what the experiment happened was he took 2 mirrors. He started moving from 1 meter to 6 meters. And there is the fact that Betelgeuse is partially coherent. So what I mean by partially coherent is, if we extend, meaning if there is 2 sources which are very close and they seem to produce a very nice fringes. And if there seems to be 2 sources here and here, suppose, they destructively interfere. Okay, that is all we want to know about partially coherence. So similarly he used that fact and he put 2 mirrors and he interfered and he started moving this mirror from 1 meter to 6 meter. Particularly at 3 meters, he observed that there is no fringe, meaning all the waves has been destructively interfered. Okay, that is how he calculated that at a particular baseline of 3 meters, at a wavelength of 550 nanometers, there is then that's why he calculated the Betelgeuse angular size. Okay, so we have seen this. Okay, here comes the. So how many of you know Fourier transform? Okay. So since a lot of people are not aware of Fourier transform, I'll not go deep into it. It's like some kind of a very interesting mathematical tool. Okay. So I'll tell you what are the major steps involved in interferometry, and after this session maybe you can go learn about it or take a course about Fourier transform and then learn about interferometry. So the steps involved is, first thing, the antennas collect the signals. Each antenna collects separate signals and then they do this multiplicative thing. Okay, and then they multiplicate and then they average it. So in normal interference we get the average, right? So similarly they multiplicate it and they do average on every baselines. We have an array of elements, so they take each data and they average it. Okay, and then so this second step also has a fancy term called correlator. You can go and check it out. And the third step is Fourier transform. So it's something like this. You take a music, okay, and this music will have song, drums beat, flute. Each has a different frequencies. Okay, so now what I'll do is take these frequencies and I'll mix one other song. Okay, so why am I doing that? Because in interferometry, when I try to do this array, I'll be getting only one pixel. Suppose there is an image which has a lot of pixels. One baseline is only giving me a particular pixel. Now I want to gather this information so that I'll get an entire image. Okay, this is the basic thing which people wanted to do in interferometry, and using Fourier transform they can easily get these frequencies and they add these frequencies and they convert back into music. Understand? So they'll suppose you take flute. I record flute separately, I'll record drums, music separately, and I add it. Understood? Because Fourier transform itself is a very huge topic. If I want to explain, it will take more than 2 hours. Okay, so this is a very basic explanation of Fourier transform. So as I did, okay, that's just turning the data. So just turning in the radio astronomical terms, we get the signal. It's already in kind of pixelated data. So we gather all these pixels and we we attach it together to fill in the gaps. So this fourth step also has a fancy name called aperture synthesis. Okay, aperture synthesis is similar to filling in the pixels. I have an image and I'll fill in the gaps with each baseline telescopes. Got it? And once now I get the frequencies and I add all the signals, now it's easy for me to turn this, the frequencies of different flute, drum, everything into a final music. So this is the process of inverse Fourier transform. So reconstructing the entire image. Anyone has any doubts? You can ask me because I have just told it very in an overall view. If you have any doubts, you can ask me. No? Oh, great. So yeah, it's Fourier transform. It's some kind of white magic. I cannot tell it black magic because it's not that. It's a white magic. It's a very beautiful mathematical tool. So everybody can go and look upon. This is an overview of interferometry, the entire process. I have been using a lot of fancy terms here: visibility data, UV plane, angular domain. Everything is very fancy. But when you try to understand, it's very beautiful. Okay, so first you take radio waves. I'll repeat once again, so you can go and look upon in any other sources. Because when I was trying to understand, first I didn't get an overall picture of what is happening. So when you get an overall picture, it's very easy to understand each and every step which is happening. Okay. So first step is I take radio waves. I have multiple antennas. I collect the data. Second step is I multiply each data, means a baseline. I multiply each data and I get each pixel. Imagine as each pixel. Okay, that is called correlator. And then what I do is I cannot, if I try to add one music to the other music, it's very bad, right? So suppose take a song and trying to add with another song. It's kind of give you a very bad music. But when you try to take the frequency, I'll take flute music, I'll take drum music, I'll try to combine it, it'll give me a very nice music, isn't it? So that's why we convert this song into different frequencies. And then we add them. Okay. And that's why they're added. And then once we are done with adding, I'll convert this data or the frequencies of music into final song. Got it? That is inverse Fourier transform. I have been using this term of visibility. So that is nothing but the specific intensity which I was talking about. Okay. So this is the overall picture of interferometry. And the future of radio astronomy. So as you've seen that there are a lot of people who are very interested in radio astronomy. So this is one such thing. This is square kilometer array. So what they do is they take dipole antennas, especially for observing radio waves at 21 centimeters. That's very important, right? That's what we all wanted, to map the universe in 3D figure. Right? We'll take a specific frequency and we'll try to image that particular space at that particular time. Okay, that's all we are doing, and these are all the kind of examples of what people are doing. This is very large array, and different shapes of antennas have been introduced in nowadays. But all we follow is the same technique of processing data. Alright, got it? So that's it for today, and very thanks for all of you for coming for the very special thanks to Sauvik Bhaiya. He explained us everything in a short span. And all on our heads and thoughts and headsets and you people, everybody, a special thank you.
Before going, I would like to correct myself. In the 21 centimeter, I told you that after the redshift it becomes 21 centimeter. It's wrong. Before redshift it was 21 centimeter. And at last, I also want to say thanks to Sauvik Bhaiya, Vatsal Bhaiya, Tanisha and all of you who come here. Thank you, all of you. Thank you. At last, I want to add one note. Learning is a non-linear process. Even if you didn't understand a lot in today, it's fine. Just keep on learning.